continue. Let me open the table of content first. Wait, okay. Alright, now we are gonna take a look at this chapter 27, interlude thread API. Okay, where is it? This one, interlude thread API. This chapter briefly covers the main portion of the thread API. Each part will be explained further in the subsequent chapter. As we saw how to use the API, more details can be found in various books and online sources. Okay, this one. We should note that the subsequent chapter introduces the concept of logs and condition variables more slowly with many examples. This chapter is thus better used as a reference. Okay. The subsequent chapter introduces the concept of log and condition variable. Wait, I'm kind of curious. What subsequent means, I guess. Okay. Maybe we can think of this as the next chapter. Introduce the concept of log and condition variables more slowly with many examples. So this chapter better used as a reference. How to create and control threads. Okay. What interface should the operating system present for thread creation and control? How should this interface be designed to enable ease of use as well as utility? Okay. The operating system present for thread creation and control. How should this interface be designed to enable ease of use as well as utility? Thread creation. The first thing you have to be able to do to write a multi-thread program is to create new threads. And to some kind of thread creation interface must exist. Right, in POSIX, it is easy. There's this API, I guess. Pit thread create. This declaration may look a little complex, particularly if you haven't used function pointers in C, right? I think this one, right? This is the function pointer. What is it called? The pointer name is start routine, and then this is the, what is it called? The parameter of the function, the type of the parameter for the function pointer, and then this one is, what is it called? The return value of the function. So to put something in here, we need a function with return value pointer void and the argument, what is it called? The argument void pointer 2. or the parameter void pointer to. Something like that, but actually it's not too bad. There are 4 arguments: thread, attr or attribute, I guess, start routine, right, this one, and arc, this one. I assume this is the argument for the function start routine here that we will use. The first thread is a pointer to a structure of type pthread underscore t. We will use this structure to interact with this thread, and thus we need to pass it to pthread create in order to initialize it. Okay. Using this structure to interact with this thread. Okay. So we declare the thread with this type, right? And then we initialize the thread using this pthread create. To initialize the value for this type pthread underscore t. The second argument, attr, is used to specify any attribute this thread might have. Some example include setting the stack size, to specify any attribute this thread might have. Some example include setting the stack size, or perhaps information about the scheduling priority of the thread. Oh, okay. Maybe we can control which thread running first using the scheduling priority. Maybe. Oh. An attribute is initialized with a spirit call to. Okay, an attribute is initialized with a spirit call to pthread atr init or attribute init, I guess. See the main page for the tile. What is it called? Okay, we have POSIX1 and the standard library. POSIX thread library. Okay. Initialize and destroy thread attribute object. Pointed to by attr with default attribute values. After this call, individual attribute of the object can be set using various related functions, and then the object can be used in one or more pthread create calls that create threads. Calling pthread attr init on a thread attribute object that has already been initialized result in undefined behavior. So we need to be careful that we need to make sure that the thread attribute have not been initialized before. Okay, object is no longer required. It should be destroyed using the pthread attr destroy function. When the thread attribute object is no longer required, destroying a thread attribute object has no effect on threads that were created using that object. Okay. Once a thread attribute object has been destroyed, it can be reinitialized using pthread attribute init. Any other use of a destroyed thread attribute object has undefined result. Yeah, we have too much undefined here. Anything can happen at that point. Okay. Oh, this is interesting. On Linux, this function always succeeds, but portable and future-proof application should nevertheless handle a possible error return. No, man. Does that mean we run out of memory? Maybe. As opaque. Okay, any access to the object other than via pthread function is non-portable and produce undefined result. Okay, interesting. Is there any error? Oh no, okay. So there is that to initialize the attribute here for the second parameter, and we use constant or const here, so we can be sure that nothing changed, I guess. In this, what is it called? Argument, maybe something like that. At least the pthread value. Okay. Some example in code setting. Okay. However, in most cases, the default will be fine. In this case, we will simply pass the value null in. The third argument is the most complex, but it's really just asking which function should this thread start running in. In C, we call this a function pointer, and this one tells us the following is expected. A function name start routine, right? It is passed a single argument of type void. This one, and then okay, as indicated in the parenthesis after start routine, right after start routine here, this one, the parameter type for the start routine function, something like that, and which returns a value of type void pointer. This one, this is the return type for the start routine function here. If this routine instead required an integer argument instead of a void pointer, the declaration would look like this, right? This one. The return type is still the same, but we change the parameter type or the argument type here to be integer instead of void pointer, state of a void pointer. If instead the routine took a void pointer as an argument but returned an integer, it would look like this. Right, we change the return type here. Instead of void pointer like this one, we change that to integer, but we still preserve the parameter type or the argument type as the void pointer. Finally, the fourth argument, arg, is exactly the argument to be passed to the function where the thread begins execution. The fourth argument, this one, is exactly the argument to be passed to the function where the thread begins execution. It is this one, I guess. Okay. Which function should this thread start running in, right? And the arg here, the argument here, the argument to be passed to the function where the thread begin execution. So the argument for this, what is it called? Function, something like that. You might ask, why do we need these void pointers? Well, the answer is quite simple. Having a void pointer as an argument to the function start routine allows us to pass in any type of argument. Having it as a return value allows the thread to return any type of result. Yeah, that's why we use the void pointer here. Let's look at an example in figure 27.1. Here we just create a thread that is passed to argument packaged into a single type. We define ourselves, this one. We just create a thread that is passed to argument packaged into a single type. We define ourselves. The thread, once created, can simply cast its argument to the type it expects and thus unpack the argument as the side. And there it is. Once you create a thread, you really have another live executing entity, complete with its own call stack, running within the same address space as all the currently existing thread in the program. The fun to begin. Okay, guess this one, figure 27.1, creating a thread. Okay, right. Let me read this first, I guess. Include this. So we get struct here and put that in type def. Okay. This is the, what is it called? The start routine function here. The function that we will put in this pthread underscore create argument. And if you take a look, we have return type void pointer and what is it called? Parameter type void pointer 2. And then this is, what is it? Casting, I guess. Because we are using void pointer, we need to determine what type the pointers point to, before we can use any data we pass in here. So that's why we do this. I think we don't need to cast like this and can just do it like this maybe. I kind of forgot. Where is it? I think chapter 26. Maybe this one. Right. We are passing, what is it called? We are directly passing the void pointer to another pointer type. In this case, a pointer to constant character, constant char. Okay, and let me try compiling that, I guess. This one T1, okay. Pedantic. Yeah, I like to use pedantic to make it portable, maybe something like that. As far as I understand, which might be wrong. Okay. At least with this configuration, there is no warning, right? Or even error. So there is that. We can just put the void pointer into another variable with the specified pointer type. And then we can use that here. Return null, okay. Yeah, I'm kind of curious. How do we use the return value for the start type here? Start routine here, I mean. Yeah, I'm still not sure about that. And to put the function pointer, we just need to put the, what is it called? The function name. So every function here, as far as I know, they have their own memory address or something like that. So we can pass that memory address with the function name like this. Okay. Oh, bitrate. Okay. But we didn't initialize anything. Did I do the same? Probably. Yeah. Oh, okay. This is, what is it called? How to control the bitrate, I guess. The thread. After we initialize the thread using bitrate underscore grid here. Be something like that. Yeah, I'm kind of confusing this first parameter with the second parameter here. It is the attribute, right? I thought that we can just what is it called? Declare the attribute, but yeah, the attribute is null in this case. And then this is the argument for this my thread function or the start routine function here. Something like that. Okay, this, wait, let me read this first. The thread completion. The example above shows how to quit a thread. However, what happens if you want to wait for a thread to complete? You need to do something special in order to wait for completion. In particular, you must call the routine pthread join. Okay, thread join the thread information here, and then pointer to void here. Okay. This routine takes two arguments. The first is of type pthread_t and is used to specify which thread to wait for. This variable is initialized by the thread creation routine. When you pass a pointer to it as an argument to pthread_create, if you keep it around, you can use it to wait for that thread to terminate. Is initialized by the thread creation routine. Okay. Yeah, when we pass a pointer to it as an argument to pthread_create, this one, we are filling some information from this function to this variable, something like that. If you keep it around, you can use it to wait for that thread to terminate. The second argument is a pointer to the return value you expect to get back. Is a pointer to the return value you expect to get back. Okay, maybe from this return, I guess. Maybe. Because the routine can return anything, right? It is defined to return a pointer to void because the pthread_join routine changes the value of the pass in argument. You need to pass in a pointer to that value, not just the value itself, right? It's like we are, what is it called? It's like we are passing the memory address to the what is it called? To the variable instead of just passing the memory address inside the pointer, you know. How do I explain this? Maybe something like this, 69, right? And then if we have something like this, we are, what is it called? We are returning the memory address from this variable, right? And then if we do this, yeah, maybe something like this. Maybe we are returning the, what is it called? The memory address of B variable here instead of the memory address of E, if I understand correctly. Did I have some what is it called? Playground maybe? Pointer to pointer, or maybe not. Yeah, maybe not. Yeah, we can try that, I guess. How many? Okay, yeah, they have that. Maybe something like this. Yeah, something like this. And then something like this. And then something like this. At least it compiled, right? And then if we if we're trying to get the value here, we can do something like this. If I remember correctly, okay, right. So yeah, this is the pointer to pointer. Or maybe we can do something like this. I'm not sure if we can do that. If we can do this, probably not. I mean, let's find out. Right, we cannot do this. Okay, in case you are wondering what this pointer to pointer means, or maybe I can, what is it called? Make an example, I guess. Something like this. Sample the argument return yeah, let's keep it simple. So this one, okay, we can try this example pointer to pointer, and then remove that. Okay, it compiled. Wait, is there any warning? No, okay. Yeah, something like this. And if we do this, right, which means we are passing the memory address of A instead of passing the memory address of a pointer, we will get an error. I don't think. Right. pointer type. Expected pointer to pointer integer here. The argument is this one, right? Pointer to integer instead. It is in this case the memory address to this a variable. Something like that. Okay. Change the value of the pass-in argument. You need to pass in a pointer to that value, not just the value itself. Right? That's why we need to pass pointer to pointer. Let's look at another example. Figure 27.2, page 4. In the code, a single thread is again create and pass a couple of arguments via the my_arg_t structure to return values. The my_ret_t type is used. Once the thread is finished running, the main thread, which has been waiting inside of the pthread_join routine, the main thread which has been waiting inside of the pthread_join routine then returns, and we can access the value returned from the thread, namely whatever is in my_ret_t. Note, we use wrapper function here. Specifically, we call malloc and then p with the uppercase p here, _join, and pthread_create with uppercase p. We just call their similarly named lowercase version and make sure the routines did not return anything unexpected. Right? Basically, the wrapper with the assert, if I remember correctly, this one, the assert function here, it is basically checking the return value of this one pthread_join or pthread_create with lowercase p, whether it returns 0 or not, something like that. I mean, if we take a look, the return value, see, the return value on success of pthread_create returns 0. So if it is not 0, it is most likely an error. Something like that. So that is what the wrapper function here do. Then return, and we can access the values returned from the thread, namely whatever is in my_ret_t. A few things to note about this example. First, oftentimes we don't have to do all of this painful packing and unpacking of arguments. For example, if we just create a thread with no arguments, we can pass null in as an argument when the thread is created. Okay. oftentimes we don't have to do all of this painful packing and unpacking of arguments. For example, if we just create a thread with no arguments, we can pass null in as an argument when the thread is created. Similarly, we can pass null into the pthread underscore join if we don't care about the return value from the function, I guess. Right. From the start routine function here. Where is it? This one. Maybe we can get this, what is it called? The return value after running this thread. After running this routine or function in the thread. Maybe something like that. But if we don't care about return value, we can pass null to the second argument in here. I think I have that as an example. Yeah, this one. Because the routine here, right, where is it? The routine here, return null. So I don't really care about the return value that the function in the thread execute. Something like that. So we can pass null as the second argument or parameter for the pthread underscore join. Something like that. Okay, this is figure 27.2, waiting for thread completion. Yeah, this is the same, right? My arc, my red. This is the argument. This is the return value. This one. All right. Okay. He allocate some memory, I guess. Okay, and then we put that. Input some value. That memory and then return the, what is it called? Return the data, maybe something like that. This make me wonder, do we need to, what is it called? To cache this, to cache the value, to cache the type, the void pointer. Maybe. If we thread here, the argument here, create join, return, okay. Oh. Right. What is it called? We put the memory address of the variable itself, not the content inside those variable or the pointer. Okay. Then printed and then free. Second, if we are just passing in a single value, for example a long int, we don't have to package it up as an argument. Package it up as an argument. Okay. Figure 27.3, page 5. So an example. In this case, life is a bit simpler, as we don't have to package argument and return values inside of structure. Okay. Third, we should note that one has to be extremely careful with how values are returned from a thread. Specifically, never return a pointer which refers to something allocated on the thread's call stack. Oh, okay. Right, for example, like we return the local variable, something like that. Like in this case, instead of using malloc, we are just using this as a local variable, right? Yeah, maybe something like this. Again, I'm giving the bad example, I guess. For my thread, my red t and false. We are using the, what is it called? The local variable instead of dynamic memory allocation here. And we can do this. And then we return that. File. Yeah, don't do this, because this have what is it called? Automatic lifetime, which means after we done with this function, the data here will be cleaned up automatically. So don't do this. Okay. See, never return a pointer which refers to something allocated on the thread's call stack. If you do, what do you think will happen? Think about it. Well, probably something like dangling pointer, where we are trying to access address or memory address that no longer exists, something like that. Here is an example of a dangerous piece of code modified from the example in figure 27.2. This one. Yeah, something like this. Okay. Alright, we can also do this. Just, what is it called? But then what is the point of this? I mean, the problem is start from this, right? We didn't really use anything from the argument here. Yeah, I just realized that, yeah, if we do this, right, which means we are allocated the variable on the stack that have automatic lifetime. And what I mean by automatic is that after we finish this function, any data in this function will be cleaned up automatically. See? Kind of similar to what I did here. So don't do this. What is it called? Do not return the memory address from local variable here. In this case, the variable oops is allocated on the stack of my thread. However, when it returns, the value is automatically deallocated. That's why the stack is so easy to use after yeah. When it returns, the value is automatically deallocated. And thus passing back a pointer to now to a now deallocate variable will lead to all sorts of bad results. Certainly, when you print out the values you think you return, you'll probably, but not necessarily, be surprised. Try it and find out for yourself. Okay. Fortunately, the compiler GCC will likely complain when you write code like this, which is yet another reason to pay attention to compiler warning. Right. Finally, you might notice that the use of vthread_create to create a thread followed by an immediate call to vthread_join is a pretty strange way to create a thread. Oh. The use of vthread_create to create a thread followed by an immediate call to vthread_join is a pretty strange way to create a thread. In fact, there is an easier way to accomplish this exact task. It's called a procedure call. Clearly, we will usually be creating more than just one thread and waiting for it to complete. Otherwise, there is not much purpose to using threads at all. We will usually be creating more than just one thread and waiting for it to complete. Otherwise, there is not much purpose to using threads at all. We should note that not all code that is multi-thread use the join routine. For example, a multi-thread web server may create a number of worker threads and then use the main thread to accept requests and pass them to the worker indefinitely. Such long-lived program tools may not need to join. Okay. However, a parallel program that creates thread to execute a particular task in parallel will likely use join to make sure all such work completes before exiting or moving on to the next stage of computation. Okay, let me read Figure 27.3. Simpler argument passing to a thread. Okay, my thread, alright. Long in value, okay. Okay, interesting. Now that is interesting. We can do this. Oh, okay. If we are just passing in a single value. Oh, but then again. Okay. It looks like we are passing the value here plus 1. You know what? Let's try this on the next session, I guess. I'm kind of curious about this one. Okay, so I guess that's it for now. Thank you for watching and see you next time. Bye bye.